Welcome to the deep dive. We take the information you're curious about, dig in, and pull out the really key insights. Today, we're jumping into some pretty cutting-edge AI stuff, prompted by our listener, the learner. Yeah, you mentioned wanting those aha moments, getting up to speed quickly but thoroughly without getting buried in data. Well, I think we've got a big one today. We're looking at this research paper you sent, Absolute Zero, Reinforced Self-Play Reasoning with Zero Data. Our mission, really, is to understand this absolute zero concept. The paper claims AI can learn to reason with, well, zero human examples. Sounds pretty wild, right? Almost sci-fi. And the implications for AI learning could be huge.
Oh, absolutely. It really turns a lot of standard AI training approaches on their head.
Eh.
For so long, the default has been, feed the AI tons and tons of human-labeled data. This paper suggests, well, a totally different route, one that might actually help us get past the limits of that data-heavy method.
Okay, let's get into the nuts and bolts then. The paper starts by contrasting this with the usual ways of training AI reasoning. Can you give us a quick rundown of what they call supervised learning and this RLVR thing, reinforcement learning, with verifiable rewards?
Sure. So supervised learning is like showing the AI the test answers beforehand. You give it a problem, the steps to solve it, the correct answer. It learns by basically copying those examples.
Okay, learning by example. Makes sense.
Then RLVR is a bit different. It's more like giving the AI a problem and a check or something that says, yes, that's right, or no, that's wrong. The AI tries different things, gets rewarded for correct outcomes. And they mention a zero RLVR variant too, which is interesting. It skips the initial human demos of how to reason.
Right. But even in that zero RLVR, we're still providing the problems and the checker, the definition of correct.
Yeah.
Humans are still in that loop.
Precisely. Yeah. Both methods fundamentally rely on us humans creating those initial questions or examples.
Yeah.
And as AI gets smarter, making enough high-quality data becomes a massive job, a real bottleneck. The researchers argue this data dependence could really slow things down, kind of like we saw with pre-training data for LLMs.
Okay, so that brings us to absolute zero. It throws out the pre-made problems, the human examples. What's the big idea here?
The core idea is it flips the script completely. The AI agent basically teaches itself. It proposes its own tasks, tries to solve them, and learns from interacting with an environment that can verify the answers. And the key thing, the really radical part, is zero human-curated data in that learning loop. None. It's learning purely from self-play.
Wow, that's kind of mind-bending. Like a student deciding not to use the textbook exercises, but instead making up their own practice problems and figuring them out.
Exactly like that. It's a great analogy. And the paper calls this the absolute zero loop.
Mm-hmm.
Can you walk us through the stages of that loop? How does it manage to propose tasks and learn from them?
Okay, yeah. So you have the agent, which is a language model in this case, and it plays two roles, proposer and solver. The proposer comes up with a task. But it's not random. It's trying to generate tasks that are good for learning, optimized for learnability, they call it.
That's a crucial bit, right? It's not just any task. It's trying to propose stuff it thinks will actually teach it something useful.
Right. So task proposed, then it goes to the environment. The environment checks if the task is valid and provides the correct answer, the gold label. And the proposer gets a reward here too, based on how learnable that task was predicted to be.
Interesting. Rewarding the proposing part itself.
Yeah. Then the solver takes that same task and tries to solve it. The environment checks its answer against the gold label, gives the solver a reward based on correctness. And the whole thing, both proposing good tasks and solving them correctly is trained using reinforcement learning, like a reward system pushing it to get better at both jobs through trial and error. Figure 2 in the paper really shows the difference visually. Absolute zero versus the old ways. You can see the human data pipeline is just gone.
And the biggest potential upside of this loop, what do you think it is?
For me, it has to be tackling that scaling problem we talked about. If the AI can generate its own curriculum, essentially, especially if it gets smarter than us, we're not the bottleneck anymore for creating training material. It could just keep going, keep improving itself, theoretically anyway.
That's definitely the grand vision. But it's not just theory, right? They actually built a system. Tell us about the AZR, the Absolute Zero Reasoner.
Right, exactly. They didn't just stop at the concept. They built the Absolute Zero Reasoner, AZR. They focused it on coding tasks using a code executor as the environment, which makes sense because code execution gives you clear, verifiable results.
Yeah, pass or fail, very clear feedback.
And AZR learns by creating and solving 3 kinds of coding problems: deduction, abduction, and induction.
Okay, can you break those down? What do they mean in terms of code?
Sure. Deduction is basically, here's the code, here's the input, what's the output? Pretty straightforward logic. Abduction is more like detective work. You have the code and maybe the output, and you have to figure out the missing input that produced it, or some other missing piece. And induction is synthesizing, actually writing a program based on input-output examples and maybe a description of what it should do, like finding the pattern or rule. And the really cool part, is that AZR learns to both create these tasks and solve them for all three types without us showing it how first.
And it's the same AI model doing both the proposing and the solving for all these task types.
That's right. So for deduction, AZR, the proposer, makes a program and an input. Then AZR, the solver, tries to predict the output. The environment runs the code, gives the real output, and boom, feedback. And the rewards are key. It gets rewarded for solving correctly and for proposing tasks that are actually useful for learning not too easy, not too hard, and diverse. They mention other research on task difficulty being important.
Okay, and you mentioned diversity. How does it make sure it doesn't just propose the same easy problem over and over?
Good question. It avoids getting stuck by conditioning on the tasks it's already generated. Basically, it looks at its recent history and is prompted to create something different, to explore the problem space more widely.
So it's building its own curriculum on the fly, driven by rewards. Okay, the crucial question then. How well did it actually work? What was the performance like after all this self-training?
This is where it gets pretty mind-blowing, honestly. Despite zero human-curated data for reasoning, AZR performed remarkably well on standard math and coding benchmarks. Table 1 in the paper is, well, you should look at it. AZR is competitive with, and sometimes better than, models fine-tuned specifically on human expert data for those domains.
Wow. Okay, hold on. Better than models trained on human expert data.
Yeah. That's what they report. And what's truly amazing here, isn't just the score, but how it got there. Without being explicitly taught reasoning steps by humans, it suggests a different path to intelligence than just imitation.
That is significant.
Yeah.
Any specific results that jumped out at you from that table?
Definitely. The AZR Coder 7B model hit state-of-the-art for its size on the overall average and the coding average scores. It actually beat previous top models that were trained on curated coding datasets. That's a big deal. They also found the starting model mattered. Using a base model that already had some coding ability, the coder variant, generally led to better results after AZR training.
Ah, interesting. So some initial competence in the domain seems to help bootstrap the self-learning process for broader reasoning.
Seems like it, yeah.
And did it scale?
Yeah.
Did bigger models trained this way do better?
They did. Figure 6 and Table 5 show clear improvements across model sizes, 3 billion, 7 billion, 14 billion parameters. All showed big gains compared to their base models. So it's not just a fluke with one model size. The approach seems to scale up.
Fascinating. What about qualitative stuff? Did the models show any interesting behaviors beyond just getting scores?
Yeah, they did observe some really cool emergent things. Like for the induction task writing code, the models sometimes generated comments that acted like step-by-step plans, almost like that React reasoning style people talk about. Figure 19 shows an example. It suggests the model is developing some kind of internal structure for solving problems, not just pattern matching.
So planning emerged on its own.
Apparently so. They also mentioned seeing cognitive behavior like state tracking in one of the llama models they tested. Figure 26 has that. But there was also an uh-oh moment, as they put it.
Oh, what was that?
Figure 32 shows an example where one of the larger models produced a concerning reasoning chain. Nothing harmful happened, but it highlighted the need for serious work on safety and alignment in these kinds of self-improving systems.
They flag it themselves as critical future research. Right. Safety is always paramount, especially with systems that learn autonomously. What about the different parts of AZR? Did the ablation studies show anything important?
Yeah. Table 2 has the ablations. They showed that all three task types, deduction, abduction, induction, were pretty important for overall performance, especially on math problems.